All right, so welcome to Chapter 18, which will be Aqueous Ionic Equilibrium. You could also refer to this chapter as buffers, but that's just actually a major component of the chapter that falls under Aqueous Ionic Equilibrium. So this is going to be part one. It will be a two-part lecture, and without further ado, we'll get it started. So let's start discussing buffers a little bit. What is a buffer? So a buffer is a solution, an aqueous ionic solution, which resists change in pH when you either add acid or base to it. And this is typically developed from two different possible combinations. One, it either contains a significant amount of a weak acid and its conjugate base, or a significant amount of a weak base and its conjugate acid. Either of those two combinations will produce a buffered solution. And buffers are incredibly important for tons of processes, but in particular biological processes. A really good example would be our primary blood buffering system, which is our bicarbonate carbonic acid buffering system. And this is a great example of the bicarbonate being our H2CO3, which is our weak acid, and then the conjugate base to that weak acid is our carbonic acid, or HCO3-. And I'm not going to get too much into the weeds with this particular system, but this is actually a multiple equilibria system which terminates with breathing CO2 out, and the rate of exhalation actually drives the equilibrium process via Le Chatelier's principle. And even though this buffering system isn't perfectly attuned to our biological pH, which we'll see more of as we get into this chapter what those criteria are, because of the coupling of multiple equilibria and the fact that we can change that equilibria through the rate of exhalation of CO2, it makes it a very, very functional buffering system. So there's a little bit more detail on that in the book, and if you're interested in this kind of thing and biological implications of chemistry, which I would hope most of you are, go ahead and look that system up and explore a little bit. Okay, so moving along, how do we make an acidic buffering solution to start? We'll start with the acidic buffer solution, and eventually we'll move on to the basic buffer solution. So under this particular example, it contains a significant amount of both a weak acid and its conjugate base. And what we'll see as we get into the weeds a little bit more here, you have to have both together. If you have a lot of weak acid but not much conjugate base, you're not going to have much capacity for the buffer to react to a change in pH from a strong acid consuming that little bit of conjugate base. So you want to have a substantial amount of both the weak acid and the conjugate base in solution together, and equal molar concentrations are ideal. Just because they're not equimolar doesn't mean that you can't have a good buffering system. It's just not as ideal as it would be if you were equimolar to begin with. So let's take a look at this classic example where we have acetic acid, which is our Erlenmeyer on the left, and that's our weak acid. Acetic acid is our primary acidic component of vinegar. It has a single acidic proton right over here. And then if you deprotonate that, you have acetate, the C2H3O2, which has a negative charge, a single negative charge, and that is in the case of sodium acetate coupled as a sodium salt to Na+. So in solution, remember, these dissociate. So sodium acetate dissociates into free sodium cation and acetate anion. And the acetic acid is in an acidic equilibria, where it's not a strong acid, so it doesn't fully dissociate spontaneously. But remember that, let's see here, I can do this. HC2H3O2 spontaneously, partially, and reversibly dissociates into protons plus acetate. So all of this is going on in solution simultaneously, and that's what we see below, is because of the reversibility of the acetic acid dissociation, you're going to have non-dissociated acetic acid, you're going to have acetate from the dissociation of the acetic acid and the dissociation of the sodium acetate. You'll also have the dissociated acetic acid reacting with water to form hydronium, and we'll have free sodium cations. So this is all going on in your acidic buffer solution. So when we add a strong base to this system that we just described, it's going to react neutralizing the weak acid in the buffer. So the buffer has both weak acid, in this case acetic acid, and acetate. Now, the acetate is our conjugate base. So when we add the strong base, it's not going to prefer this conjugate base. It's going to prefer reacting with the acid, because acids and bases like to react with one another. So in this particular example, our sodium hydroxide, which is aqueous, is going to have our hydroxide, and it's going to react pulling off the acidic proton from our acetic acid. And this is going to form an equivalent of liquid water. And then we'll have acetate and sodium, and these will form an aqueous salt. So in solution, these are going to be dissociated with free acetate and free sodium salt, but we can draw it as an aqueous salt, like we see here with our sodium acetate. So what we've done is we've consumed one part of the buffer to make the other part of the buffer. We're consuming our weak acid here with the base, and that's making the conjugate base to that weak acid as a product. And this resists the change in pH, because instead of just adding base to solution, this base is now being consumed and creating a much weaker base. Now, the caveat to this is the amount of sodium hydroxide that is added has to be less than the amount of acetic acid present, because if you have more sodium hydroxide than acetic acid, it will completely consume the acetic acid. You will no longer have acetic acid in solution, and the remaining hydroxide will directly affect the pH. But as long as the amount of hydroxide being added is less than our acidic buffering component, it's going to resist that change to pH. Another really important thing to consider here is remember that we have this weak acid, which is reversibly dissociating into free protons or hydronium if we were including water on both sides of the equation here. In acetate. And if we look above, when we add the sodium hydroxide and it reacts with the acetic acid here, that's going to be functionally adding acetate into our products. And based on Le Chatelier's principle, this will drive the reaction back towards reactants, which is our acid. So conveniently, even though we're consuming the acid with our strong base, we are actually resisting pH through two mechanisms. One, by preventing free hydroxide from floating around in solution and making a weaker base in the form of our acetate, and by adding that conjugate base into the mixture, Le Chatelier's principle is driving the reversible reaction back towards our weak acid, and this doubly resists the change in pH that we would see. Likewise, if a strong acid is added, it's going to neutralize the conjugate base component of the buffer. So remember, the buffer had two components. It had the weak acid and the conjugate base. The first example we were looking at what happens when we add base. But in this particular case, we're adding acid. And so what it's going to do is it's not going to come after our weak acid first. It's going to come after our conjugate base in the buffer. So let's take a look at this. We have hydrochloric acid, which is a strong acid. It's going to fully dissociate into free protons and chloride anions. And then we have, so we can think of this as functionally protons floating around in solution. And that strong acid is going to attack our acetate, and it's going to form our weak acid, our acetic acid, and sodium chloride as a salt byproduct. This is functionally analogous to what we just discussed. Once again, as long as the amount of hydrochloric acid that's added is less than the amount of sodium acetate or conjugate base present, the pH is going to be small, because it's all going to be consumed by reacting with the conjugate base. This is going to prevent the addition of just free protons into solution, and it's going to drive that equilibrium process that we were looking at before via Le Chatelier's principle back as well, which is going to further resist our change in pH. Now, there's a, actually, and let's elaborate on that a little bit. So buffers work by applying Le Chatelier's principle to weak acid-base equilibrium. It's not just the scavenging of the acid you're adding or scavenging the base you're adding to solution. You're actually just resisting pH by pushing the equilibrium via Le Chatelier's principle. So if a buffered solution contains significant amounts of weak acid molecules, generically HA, where this is our generic weak acid, where HA spontaneously dissociates into acid plus conjugate base. With this designation, these molecules are going to react with any base that is added to neutralize it. So we have our weak acid HA and we add hydroxide. This hydroxide is going to pull the proton off that acid very aggressively, producing liquid water, and produce our conjugate base A-. And this could be drawn with water present as well, scavenging hydronium. But we also have significant amounts of the conjugate base floating around in solution. So these ions are then going to combine with any acid that we make, add to solution, and drive that back towards acid. So after the equilibrium shifts from either of these arrangements, the concentration of hydronium is going to be functionally constant. I mean, that's another overstatement. That's not constant per se. It's just going to be highly resistant to significant changes, as long as the solution is in a buffered state. So one other thing to keep in mind here is an effect called the ion effect, common ion effect, which states in a weak acid solution, adding a salt containing the anion sodium A, where A is our conjugate base, the conjugate base of the acid known as the common ion shifts the position of the equilibrium to the left or back towards reactant. And this makes sense. So let's say we have our generic weak acid reversibly dissociating into proton plus conjugate base. If we then have an Erlenmeyer and we're pouring a solution of sodium A, which in aqueous solution is functionally equal to, sodium and our conjugate base A, we're functionally adding in conjugate base. Well, if we're increasing the level of our conjugate base in this equilibrium, that's going to push our equilibrium back towards our reactant, or in this case to the left, and this is going to go towards our weak acid. So the addition of these sodium salts of the conjugate base are going to shift equilibrium to the left, and this is known as the common ion effect. So this lowers the concentration of hydronium ion in solution and causes the pH to be higher than it would be otherwise than the pH of the acidic solution. So this is just an interesting example of this effect taking place, where on the far left we have a 0.100 molar solution of acetic acid. On the far right, in the middle, we have a 0.1 molar solution of sodium acetate. Notice that the pH of the 0.1 molar acetic acid is 2.9 pH units, and the pH of the 0.1 molar sodium acetate is 8.9, so slightly alkaline. Now, to a novice, you would think, well, what would happen if we mixed these together? We would just meet in the middle. But that's not the case. We don't just meet in the middle. It actually tends towards the acidic side, and in this case, if we add these two solutions together, the pH is going to be 4.7 due to this common ion effect. And this is also dictated by having an equal molar solution of weak acid and conjugate base, as we'll see in a little bit further down the line in this lecture. That means that the pH is going to equal the pKa of our weak acid. And in this case, the pKa of acetic acid is 4.7. So under these circumstances, our pH will equal our pKa of our weak acid, which is 4.7 due to the common ion effect. So let's get into some math and predictive value, because that's everybody's favorite thing. We're going to do this two ways. We're going to do it from the way that we're already kind of familiar with, using the ice table, and show the applicability of that technique. And then we're going to use a new technique, which is significantly more straightforward, as long as a couple assumptions are valid. So, long way first, fast way second. Both are perfectly acceptable. So, step one to finding the pH of a buffered solution. You need to write out your equation for the acid, and then you prepare an ice table based on that particular equation. You complete the ice table, showing the given initial concentrations of the acid and its conjugate base, both of them, and you represent the change in the concentration of all species in terms of X, just like we would for previous ice tables. Then you substitute the expression for the equilibrium concentrations into K. It's very important. And then once we have those expressions substituted into the K, expressions of X substituted in for K, you can determine the concentration of hydronium or acid from the calculated value of X, and then calculate pH as necessary. Then you want to check your answer as a final step. So let's do an example of that. So right out the gate, calculate the pH of a buffered solution that is 0.100 moles per liter in acetic acid and 0.100 moles per liter of sodium acetate. And this is interesting because we already saw the answer to that in our example 2 slides ago. But let's work through it hypothetically here. So step 1, write the balanced equation for the ionization of the acid and use it as a guide. Well, here we have acetic acid, aqueous, in water, liquid, reversibly dissociates, and into hydronium, aqueous, plus acetate, aqueous. So this is our guide, right? And so we're going to set up our ice table where we're excluding liquid water because it doesn't participate in the equilibrium. So we have 3 terms. We have 1 term on the reactant side and 2 terms on the product side. On the reactant side, we've got our our acetic acid, and on the product side, we have hydronium and acetate. So we can start filling this out now. Our initial concentrations, we know. We started with an initial concentration of 0.100 moles per liter of acetic acid. So we fill that in here. And we have 0.100 moles per liter sodium acetate, or in this case acetate as well. So we fill that in, and initially, because there hasn't been any opportunity for interaction between these, we're going to assume the concentration of hydronium is near zero, or approximately equal to zero. Then we move on to step 2, which is stoichiometrically represent change with the variable x. In this case, everything reacts with a 1:1:1 ratio. Very straightforward. Therefore, we don't have to modify our x with anything, which is lovely. So the reactant will react. Therefore, over time, its concentration will decrease. Therefore, its delta is negative. So change is minus x. And for the products, both will go up plus x. Following that, we can determine our equilibrium concentrations in terms of x, with our equilibrium for our acetic acid being 0.100 minus x, our equilibrium for the hydronium being simply x because it started at 0, and our equilibrium for our acetate anion being 0.100 plus x. And now that we have all three of these terms, we can make our relationship to describe the acid ionization constant, Ka. And Ka is going to be the concentration of our products over the concentration of our reactants, raised to their respective powers, which are all 1 in this case, very conveniently. And we can substitute in for all of our terms, giving us the following relationship. And here's what's important. In most cases, you can make the approximation that x is small. And we're going to talk a little bit about this more. But as long as x is small, you can say it's not going to substantially modify the term here or here. Okay? Excuse me, not outside that. But for if x is substantially smaller than 0.100, it may not even impact the value of 0.100 in terms of significant figures. And that's what the assumption is based off of here. Excuse me. So, if x is small, we're going to just remove that plus and minus term as an approximation, and then we're going to substitute the value of the acid ionization constant from the table in the book, in this particular case, Ka for our acetic acid is 1.8 times 10 to the minus 5th. Because of simplification, the 0.1s cancel one another, and x is going to equal 1.8 times 10 to the minus 5th. Now that we have that, what we should really do is confirm that x was small to begin with by calculating the ratio of x and the number it was subtracted from in the approximation. So in this particular case, if x is 1.8 times 10 to the minus 5th, that's only 0.018% of the initial value of 0.100 moles per liter. That is a small value, and therefore the approximation is valid. That's always a good thing to do, just to double check. Now that we have that term x validated, despite our assumption that we made, step 5, determine the concentration of hydronium from the calculated value of x by substituting into the pH equation. So pH equals the negative log of the concentration of hydronium, or free protons, and we can just plug that right in and get pH equals 4.74, which is correct. Now, what I'd recommend doing, since this is all fresh in your head, instead of continuing through the video, we have a couple extra practice problems here listed right underneath. We've got one here and one here. A little bit extra work. Go back to the previous slides, set these up, see if you can get solutions for this. Just work it now instead of continuing on, because it'll really reinforce the concepts and the processes. And once you're done, jump on into slide 14. Because slide 14, we have a whole new equation, the Henderson-Hasselbalch equation. And this is what I would consider the more elegant solution or mechanism of solving the same question. Now, this also depends on x being small as an approximation. However, if x is small, this is a very slick relationship to utilize to your advantage in this chapter. So, what Henderson-Hasselbalch is an equation which is derived from the Ka expression. And I'm not going to go through the whole derivation. That's in the book. If you're into derivations, I personally am. I love derivations, but I'm never going to ask you to recite a derivation. And for those of you who are mathematically inclined and you're curious how this relationship is derived, please go down that rabbit hole. I encourage you to do so. But for those of you who just want functional knowledge on how to use the Henderson-Hasselbalch equation, it's a very straightforward equation to remember, and either approach is perfectly acceptable, whichever is your preference. So, it's derived from K expression and allows us to calculate pH of buffered solutions very easily. So what this really comes down to is that it relates the pH of a solution to the pKa of the weak acid in that buffered solution, plus a modifier to that pKa. And how the pKa is modified depends on the log of the ratio of the conjugate base over the weak acid. Pretty straightforward. So once again, this is generally a good mechanism of solution as long as x is small, and in most cases, for weak acids, this is true. We can generally say that x is small approximation is going to work if the following are true. One, the initial concentration of acid and salt are not very dilute. You have reasonably high concentrations of these because, well, I'm not going to get into it because that leans on the derivation. We're not talking about it. But as long as you're having reasonable lab bench concentrations of your weak acid and conjugate base, this is probably going to be valid. And Ka needs to be fairly small, which for weak acids, once again, is typically valid. So for most problems, what this means functionally is that the initial acid and salt concentration should be over 100 to 1,000 times larger than the value of Ka, which is something that you're going to find is typically satisfied. So, let's talk about calculating pH changes in buffered solutions. There's typically two parts of solving these problems. So let's do a couple of these. Calculating the new pH after adding acid or base requires breaking the problem into two parts. One, the first part is stoichiometry calculation for the reaction of the added chemical with one of the ingredients of the buffer to reduce its initial concentration and increase the concentration of the other. What this functionally means is an added acid is going to react with your conjugate base to make more conjugate acid, or you're going to be adding a base which reacts with the conjugate acid, or the weak acid, to make more conjugate base, just like we discussed. And then part two, an equilibrium calculation of the concentration of hydronium or free proton using this new initial value other than the concentration of our weak acid and the concentration of our conjugate base. So whenever you're calculating the pH of a buffer after adding small amounts of acid or base, remember that adding a small amount of strong acid to a buffer is going to convert a stoichiometric amount of the base to the conjugate acid and decrease the pH slightly. And adding a small amount of a strong base to any buffer is going to convert a stoichiometric amount of the acid to the conjugate base and slightly increase the pH of the buffer. These are all mental checks that you're going to need to have in place. So let's do some examples. Once again, we'll do one with the ice table. and then we'll do one with the Henderson-Hasselbalch. So problem 1 here. Calculate the pH of a buffered solution that is 0.050 moles per liter benzoic acid and 0.150 moles per liter sodium benzoate. And for benzoic acid, the the Ka is 6.5 times 10 to the minus 5, so fairly small Ka. Now note, right out the gate, we are not equimolar. We have 0.05 moles per liter the weak acid, and with 3 times that quantity, 0.150 moles per liter benzoate, which is our conjugate base. So we can write the balanced equation for this reversible dissociation, where we have benzoic acid in water reversibly dissociates, forming our hydronium plus our benzoate anion. And we're just going to set up the ice table rapidly, where initial concentration is 0.050 moles per liter of our weak acid and 0.150 moles per liter our conjugate base. Our initial concentration of protons or hydronium is 0 functionally, and the change is going to be minus x because everything's 1 to 1 to 1 in our stoichiometry, minus x for our reactant because it's going to go down during the reaction, and our products are going to go up, so they're both going to be plus x. We can fill in the blank for equilibrium by summing those quantities and then substitute in to our Ka expression, where our products over our reactants are our acid plus our hydronium times our conjugate base over our weak acid. Now, making the assumption that x is small, in this case it is, we can just eliminate x from our expressions, the plus minus expressions here, and then solve for x. And that's going to give us a fairly small value, which is going to be equal to the concentration of our acid at equilibrium, or hydronium at equilibrium. So, knowing that exact thing, we can substitute that into our pH expression. pH equals the negative log of the concentration of hydronium, or H+, and that's going to give us a pH of 4.66. We can then check that to make sure that the ratio is less than 0.05 or 5%. And that does hold true because in this particular case, if you divide 2.2 times 10 to the minus 5 over or by 0.050, that's only 0.044%, so we have several orders of magnitude of leeway in this approximation being valid. Now, our second approach to this would be using the Henderson-Hasselbalch equation. So the Henderson-Hasselbalch equation is pH equals the pKa plus the log of the concentration of your conjugate base over the concentration of your weak acid. Remember that. Lock that one into memory, guys. And remember, our weak acid, benzoic acid, our conjugate base, benzoate. So, in this particular case, our Ka is known, 6.5 times 10 to the minus 5, and pKa is just the negative log of Ka. So, let me write that down for you guys. That's where we're getting this expression here. So, negative log of Ka plus the log of concentration of our conjugate base over the concentration of our weak acid. And that's a fairly easy solution. And that agrees at 4.66. Now, having seen both these techniques, I recommend once again pause the video and work out the following solutions or these following problems. Just use this opportunity to recruit those neurons, build some long-term potentiation, and develop a little confidence, and also just to slow the input of new information for a second. So we'll pause here for a second, work some problems, and then hop into slide 22 with me. Let's look at one more example using the Henderson-Hasselbalch equation. In this particular example, what we're going to do is calculate the pH of a buffered solution composed of a weak acid and its conjugate, a weak base and its conjugate acid. So, slightly different than what we've been doing before. In this particular example, we're going to calculate the pH of a buffered solution, which is 0.500 moles per liter ammonia and 0.20 moles per liter ammonium chloride. So, in this particular example, ammonia is a base, it's a weak base, and ammonium, NH4+, well, let me lay this one out for you guys. Remember, ammonium chloride is going to dissociate into ammonium cation plus chloride anion. And ammonium is a weak acid to which ammonia is the conjugate base. Conversely, ammonia can be considered a weak base with ammonium being its conjugate acid. So knowing this now, erase all of this. And knowing that the pKb is 4.75 for ammonia, which is like pKa, but it's describing the Kb for ammonia. Since Kb for ammonia is 1.76 times 10 to the minus 5, this is going to be much smaller than any initial concentration we see in this, because, let's say, that's many orders of magnitude lower than 0.50 or 0.20. We can easily use Henderson-Hasselbalch, and we can just set it up. But first, we need to lean on, because Henderson-Hasselbalch uses pKa, not pKb, we need to solve for pKa. So if they give you Kb or pKb, remember this relationship that pKa plus pKb equals 14. So you can rearrange that to say that pKa equals 14 minus pKb, and then substitute the pKb of 4.75. So pKa is just going to be 14 minus 4.75, which is 9.25. And now that we know this, we have the pKa, we can substitute this into the Henderson-Hasselbalch equation, and we are off to the races. So, Henderson-Hasselbalch, pH equals pKa plus the log of the conjugate base over the concentration of the weak acid. And this is plug and chug, 9.25 for our pKa plus the log of 0.5 over 0.2, and solve 9.65. Not bad. I think you guys are going to like this this equation. This is a pretty easy equation to use. So, to take a quick step back, action of buffers. Remember, whenever you have an initial buffer concentration, where you have equal concentrations of weak acids and conjugate bases, like you see in the middle here, you're going to have that balance where you're going to have your weak acid molecules, which are protonated with those little gray dots on the side of the purple, and we have our conjugate base, which are deprotonated. And if we're adding acid, our example here to the left, the acid's going to react with conjugate base, and it's going to start putting protons onto the base, and you're going to see some of that conjugate base being consumed, where you're going to have extra protons being added in there. And so it's going to slightly increase the ratio of our weak acid and slightly decrease the pH of the solution, because it's going to be slightly more acidic, but it's going to have resisted the dramatic pH changes that you would have seen if we had just been adding free protons to solution in an unbuffered situation. Likewise, over on the right, what if we add hydroxide? If we're adding hydroxide, it's a strong base. It wants to react with an acid, so it's going to react preferably with our weak acid, HA, by deprotonating it. So it's going to start taking those little gray protons off. And that's what we're seeing here. We're seeing that deprotonation of the weak acid and the production of more conjugate base. Because of that, we're going to see a slight increase in the concentration of our conjugate base, and the pH is going to go up slightly because we've made a little bit more base, but it's not remotely the pH change you would see if we'd just been adding free hydroxide to solution. So, perhaps that example, that last Le Chatelier's example, could have gone after this slide, but I think it'll work out okay. You guys are pretty sharp. So, basic buffers. Most of our examples had been previously weak acid conjugate base. However, you can also form a perfectly viable buffered solution by using a weak base and its conjugate acid. And this is a great example, the one that we had in that previous example, where ammonia is our weak base and is going to be in equilibrium with conjugate acid ammonium, which will be pulling a proton from liquid water, and this is going to be forming a little free hydroxide as a byproduct instead of the hydronium ion you're used to seeing H3O plus for those weak acid examples. But everything else is identical in terms of logic. So, what makes a buffer effective? Well, what makes a buffer effective is a variety of different variables. So remember, what a buffer is doing is it's neutralizing acids or bases that are added to solution up until either the weak acid or the conjugate base is fully consumed by the base or acid, respectively, that you're adding to solution. So there's a limit to how much a buffer in solution can resist the pH change before you get those significant changes. And this is referred to as buffer capacity. So the buffer capacity is the amount of acid or base that a buffer can neutralize. And the range of a buffer is the pH range in which the buffer can efficiently operate. So these are really the two factors that define a buffer's effectiveness. It's one, the relative amounts of buffer, acid, and base in solution, and two, the absolute concentration of the buffering acid and base. So, a couple quick and easy rules to go by. A buffer is going to be most effective when the ratio of acid, weak acid, to conjugate base is 1. When you have equal molar concentrations to start with, you have the greatest ability to buffer up against both acid and base. So equal concentrations is ideal. You don't always get that, but for generalizable applications of buffers, it's best to start with equal molar concentrations. A buffer will retain its general effectiveness when the ratio of the acid to base is limited. So for a buffer to be a buffer, you have to have some of both the weak acid and conjugate base. So if you're adding acid into a weak acid buffering system and you're consuming the conjugate base progressively, you're going to start to drive up your concentration of weak acid, and you're going to be depleting your concentration of conjugate base. At the point where you have about a 10-fold increase in your weak acid and a 0.1 or a reduction of 90% to your conjugate base is about the point where you're losing your buffering capacity, where you don't really have a buffer because you're depleted your ratio of conjugate base to acid too much. That said, a buffer is going to be most effective when the concentration of acid and the concentration of conjugate base are large. And we've said this now that the ratio of the acid to base has limited effectiveness, but let's substitute in this 10 to 0.1 rule into the Henderson-Hasselbalch equation and see what the implications are for that in terms of pH shift. So if we put these values into the Henderson-Hasselbalch equation, we would see that the lowest pH a buffer would be effective would be when the pH is 1 less than the pKa. And the highest is if the pH is 1 above the pKa of the weak acid in our buffering system. So the best rule of thumb for this is that the effective range of a buffer is plus or minus 1 pH unit from the pKa of our weak acid in our buffering system. Now remember, if we go back all the way to the beginning of this lecture, which was a long time ago, to be fair, remember when we added 0.100 moles per liter acetic acid and 0.100 moles per liter sodium acetate, we developed an equimolar ratio of weak acid to conjugate base, and the pH of that was 4.7. Well, the pKa of acetic acid is 4.7. So if you go back here, and we look at log of conjugate base to weak acid, if we did that for that situation, 0.100 over 0.100, and took the log of it, what's the log of 1? It's 0. So when you have equimolar concentrations, this whole term goes away, and pH just equals pKa. So when we say effectiveness of buffer is defined by plus or minus 1 from the pKa, this also gives us information into choosing weak acids that function as good buffers at specific pH ranges. If you want to buffer a system at a target pH, you need to pick a weak acid which has a pKa plus or minus 1 within your target. So, an example, preparing a buffer. Which acid would you choose to combine with a sodium salt to make a buffered solution at pH of 4.25? Whatever reason, you need a buffer solution at 4.25. And you have a host of different weak acids you might be able to utilize. You can use chlorous acid, nitrous acid, formic acid, or hypochlorous acid. And they all have unique pKa's. But we want to pick the pKa that's closest to our target pH of 4.25 to give us the most effective buffering capacity. So, although anything where a pKa falls into plus or minus 4.25, anything from 3.25 to 5.25 could be acceptable. We want to be as close to 4.25 as possible. So let's look at this. Chlorous acid, pKa of 1.95, is out of range. It's not going to be a good weak acid to form a buffer at 4.25. Because what would happen is, well, let's take a look at that. Actually, I think we might do that in a later chapter. But if we were to put pH, remember pH equals pKa plus log of concentration of base over acid, what we can do is say if the pH is 4.25, and in this case chlorous acid, the pKa is 1.95, you could solve for the ratio of conjugate base to acid. And let's just do a quick thing here. Let's say this is 2.35 equals log of, oh, that's a terrible drawing vertically. Let me try that again. Log of base over acid. You're going to see a ratio of base to acid of over 100 to 1. So this is functionally not going to be a good buffer any longer because it's almost all one species. That's what happens when you're too far away from your buffering. You lose your buffer. Now, let's look at nitrous acid. That was a little bit of a segue. Nitrous acid, pK of 3.34. Technically, in the bottom range, could work, but formic acid's better because it's closer to 4.25. So formic acid's our winner in this case. So let's go ahead and plug this in like we were just looking at. pH equals pK plus log of the conjugate base over the concentration of our weak acid. And let's solve this for formic acid. And you can see that the ratio of base to acid is 3.24. So this is absolutely reasonable. Still retains good buffering capacity. How about we take a pause here and you guys work this exact same equation, but you do it for hypochlorous acid, where the Let's solve this exact same problem, but for a target pH of 7.35. Go and take a pause, run this problem, make sure you understand where you're going with this, and just kind of take a minute to wrap yourself around this particular concept of buffers. Then we can move on. We have a few more slides, and then we're going to take a break, and then we'll go into the second lecture. So, buffer capacity. As the ratio of the concentration of your conjugate base to the concentration of your weak acid approaches 1, the ability of the buffer to neutralize both bases and acids improves. However, if a buffer needs to work primarily with resisting acid that's being added to it, it's better to start with more base. Because if you know you're just adding acid and you're resisting acidification, you don't need to have a whole lot of your weak acid present, because that acid's going to be primarily reacting with your conjugate base in the buffer. So more base is preferable if you're only resisting acid. And in a buffer where you're mostly resisting the addition of base, you're going to want to start with more conjugate acid and a little bit less, a little more weak acid and a little less conjugate base for the exact same rationale. And so final slide, remember, buffering capacity is the amount of acid or base that can be added to a buffer without causing a significant change to pH. And what we're going to look at in the next lecture is dynamically, through titrations, how pH changes as we start adding acids or bases to buffering systems. Also remember that the higher the concentration of the components of our buffer, that being our weak acid and our conjugate base, the more of it's available to react with an acid or base that's being added to solution. So therefore, buffering capacity increases as you increase the absolute concentrations of your buffering components. And once you've consumed all your buffering components through the addition of that strong acid or strong base, the buffer has been consumed and it's no longer effectively buffering. And then you get that rapid change of pH you would expect from just adding acid or base to solution. And that's it for this lecture. I'm going to take a little bit and take a breath and get some water, and then we'll be back with the second part of Chapter 18.